stats, I just want to recap where we're at. So a couple things we've done is we've come up with conjugative analyses, and we've played around with the limit of those. We went through it pretty quick with the precision parameter, the variance analysis, however you want to think about it. I put it on the precision scale. I want to recap that real quick and talk about the results, and then talk about the joint posterior of both parameters. So far we've come up with our full conditional distributions. So this right here is the full conditional. This is a new term for mu. So just a full conditional, that's a new term. What I mean is it's the conditional distribution of mu, and it's being conditioned on everything else. Full conditional is the name that we usually talk about. We usually use these distributions in good sampling. We're not there yet. So these are useful distributions, and that's why they have names. Right now, we've been thinking about these just as kind of an intuitive basis for understanding priors and what they do. It's a distribution that we know, the normal distribution, so it's a good place to start. I like the binomial example for the sheer reason that the sampling distribution is discrete. The likelihood is continuous, and it's bounded between 0 and 1, so that's where we actually started. Most people start with this analysis. We had worked out under the conjugate prior what this was. So, have to talk about our priors before we get posteriors, but we've got a likelihood function. Now, I haven't written down which parameter this is the likelihood function over. If somebody wrote this down, they could call it a sampling distribution if they were thinking about it as a function of x. It could be a likelihood over mu, if you let mu vary and x is fixed. Could be a likelihood function over phi, let phi vary, mu is fixed. It could be a likelihood function over both mu and phi with x fixed. So that equation represents a lot of different things depending on how you use it. If we want to do inference on the mean, if everything else fixed, then I just let mu vary. If everything else is fixed, then I need to use some prior, I multiply it into it, and then I can come up with a posterior. So, under a conjugate prior, this was a normal distribution, and it had two parameters in here. So I'm going to write down the prior that we're using was normal, mu naught, and I still sometimes like to go back and forth between sigma and phi, depending on what I'm doing. So I'm well versed in both those parameters, so I can move back and forth between them seamlessly. So we had written down under this prior the mean right here. I'll just put it down notationally and we'll rewrite out what it is. So I'll write down sigma squared right here, and this was the variance of mu given x and sigma squared. So this thing is just some weighted average. This was going to be x over sigma squared plus mu naught over sigma naught squared times 1 over sigma squared plus 1 over sigma naught squared. I've got my negative sign right there, really dividing by this. That's a result we've seen plenty of times now. The variance is just this part of it. Write it down, just to be complete. If I wanted to change sigma squared in all of this, and I wanted to flip it upside down, I could just do it. So this is equivalent to x times phi plus mu naught. I'll keep this as sigma naught squared, just to show all the flexibility I have in re-expressing this. So phi plus 1 over sigma naught squared. If you want to be a little bit more traditional and not miniature notations, you could call this mu naught times phi naught. And you probably know what phi naught is. It's 1 over sigma naught squared. It's the same exact thing. I don't have to do any transformations to do any of that. So I can just plug it in. It's a fixed number. So if sigma squared was 5, then phi is 0.2. That's what it is. So nothing fancy here. I can move between these parameters because they mean the same thing, they're just on a different scale. So this all required the conjugate prior to come up with this. In the limit, we found out as sigma naught squared went off to infinity. That's the same thing as the precision parameter in the prior going to 0. Same thing happens. This is just going to be a normal distribution centered at x with variance sigma squared. You could write it down like this as well. So I want you to get used to moving between variances and precisions. Not a big deal. Why do we like it? I think it's because we like gamma distributions. We don't want to memorize the inverse gamma. If you don't care, go ahead and do it however you want. The analysis you're going to come up with using the variance and doing everything along the variance scale for this distribution will be identical to each other. I can transform between the two things because that's a one-to-one transformation. Let's rewrite out what we found last time concerning the precision analysis. Concluded about here. But I want to put a little bit more concentration into the result. I need some prior distribution on phi. So I should write down this is proportional to. So that's base, likelihood times prior. Penalized likelihood, you can think of it that way, that's base. So this thing, we already know what the formula is. We'll rederive this one more time just because it's so simple. This was phi 1/2. I'm going to get rid of my 1 over 2 pi because I don't need it for anything. I've got the proportionality sign. E to the minus phi. I'm going to write it out. X minus mu squared over 2. So that's my likelihood function. And for our conjugate analysis, well, this is the conjugate prior. On phi, the whole trick is to stare at this thing and to think, what do I multiply by? And it still has the same functional form as the thing I multiplied by. What you'll recognize is the kernel right here kind of looks like a gamma. And so the kernel of the likelihood looks like a gamma right there. So that's kind of a dead giveaway. So, but it requires recognition. So we wrote down, this is our prior. This was going to be phi to the alpha minus 1, e to the minus beta phi. And I'm going to remind you just real quickly what the normalizing constant looks like. You don't need to write it down, but since this is a little bit new to us, we probably want this part in our memory. Does anybody know what this is?
Beta alpha over gamma function alpha.
Yeah, beta to the alpha. Yes. Wikipedia on it. Thank you. That's what that is. Gamma functions, I'll remind you, it's really, how do we come up with the normalizing constant? We just need to integrate this bit and flip it over. So we have to integrate phi between 0 and infinity. And then whatever that solves to is the inverse of the normalizing constant. The typical probability analysis, this gamma function is really written down in terms of an integral. And so we don't have closed form solutions to that unless alpha is an integer. In that case, it turns into a factorial. Probably you know about that, but I would read about it on Wiki. That's how Muhammad gets all his knowledge. So he plugs his brain in at the end of the night and downloads. So we'll keep that in mind. We don't need this result for our answer. This thing right here is just v to the alpha plus 1/2 minus 1. So I'll just combine this term and this term. Now I'm going to combine the exponential. This is going to be x minus mu squared over 2 plus beta. That's it. This thing is a gamma. Alpha plus 1/2 x minus mu squared over 2 plus beta. So that's what we came up with last time. Very easy analysis. If you know what gamma's distributions are, the problem almost solves itself. And so we talked about the mean and the variance. We wrote down the mean for this. It's just this term over this term. Usually I'll re-notate this. Just call this alpha tilde over beta tilde. It's probably useful to write it down. Alpha plus 1/2 over x minus beta squared over 2 x minus mu. Too many parameters really around. So alpha plus 1/2 over x minus mu squared divided by 2 plus beta. And so we talked about the classical estimator. The classical estimator for variance is just this term on its own. We're working on the inverse scale, and that's why it's showing up in the denominator and not the numerator. And we notice that it's very similar to this answer. It's the typical classical estimator. So this is how you might estimate variance. This is a typical estimator right here for variance. Any Stat 101 class, you probably compute that thing. So they told you the mean, you do that. If you had more data points, you would average this quantity over those data points. That would be the MLE in this analysis. It's also unbiased in this case because you know mu. So you don't need to divide by the n minus 1. All things that you've probably seen or touched on before. So this answer right here is almost the reciprocal of this answer. But they're penalized by the hyperparameters in the product. And so they're penalties. How much influence do we want the prior to have? Well, if alpha and beta are big, those penalties are going to take over. They're going to swamp out the information right here. So you're inclined to think maybe these are small. So the smallest we can make them is 0. If we do that, we let alpha equal to beta go to 0, then our answer is going to be this. X minus mu squared. I'll write it like that. 1 over. So in the posterior, that's the way we're thinking of taking this limit. Okay, so that's kind of how we did it with the mean as well. We took that limit after we had multiplied everything in. The induced prior in the limit for the mean, when we ended up taking this out to infinity, what we really did is we let the prior approach a constant. It's getting flattened out. So if I multiply by 1, and I didn't keep the limit in the posterior, we'd get the exact same answer. So these are equivalent to each other. In this analysis, I'm thinking of taking alpha and beta towards 0, and I get this. The prior that we get, all we have to do is come up here and look at this function. And think about what this function is alpha and beta go towards 0. So as alpha and beta go towards 0, the prior that we're using is going to be 1 over b. So that's just b to the 0 minus 1. So that's b inverse. That's this. This part right here, as beta goes towards 0, that becomes 1. We're going to forget about the normalizing constant. And if we wanted to, we could try to derive the induced normalizing constant through this limit. What you would have to do is you would have to integrate this function right here. We can give it a shot. Between 0 and infinity, dv. Can anybody do this integral? I'm going to give you a hint by putting an arrow. What's that? It's the log, and now you have to evaluate it, because this is a definite integral. So you're going to evaluate your log, and it's going to blow up on you. So this goes off to infinity. This diverges. And we know that. Kind of one of those things we learned about in calculus class, and it's like, it keeps getting smaller and smaller, you keep adding it, but it adds to infinity. And so this is improper. What it's telling you is that this thing right here is infinity. It blows up on you. That's an improper analysis, but it matches at least a classicist analysis in some sense. Where this answer right here is equivalent to that answer in some sense. Of course, the Bayesian can put a full distribution on things, and I'm just looking at a particular point estimator in there. And so this is kind of a funny prior right here that we're using. So both of our priors in the limit become improper. What it means is I'm putting mass way out there in the tails. So I'm putting mass in a lot of places. And that seems pretty good. If you just think about Bayes as this weighted analysis, I don't want to put so much weight in my prior that I dominate the likelihood function. My whole analysis is steered by my prior. We don't want to do that. So these improper priors turn out to usually be good. I want to show you one more thing about this. If I didn't want to talk about things on the precision scale and I wanted to talk about things on the variance scale, I could just transform. So if we wanted posterior distribution of sigma squared, we transform. So what that means is everywhere I see a phi in my analysis, I plug in a 1 over sigma squared. And then I take the Jacobian, or the derivative, of 1 over sigma squared as well. Remember, you're taking the derivative with respect to sigma squared. So that notation might baffle you. And usually when I do this, I usually change this to phi. Right here, variance. Then it's like, okay, then I take 1 over v, and I take the derivative with respect to v. And you could do that. We'll do something very similar to that in just a second. And we would get this posterior. Question is what is the prior? So what is the implied prior for the variance? I'm going to call it V. You'll see why you didn't catch my thing. So note the prior, we know the prior for the precision, pi p, and I write it down like this, 1 over v. I don't even try to normalize it because it's not normalizable. This is the prior that I at least like. It doesn't put much weight into the analysis. It has the conjugate form. I feel good about all that. So the analysis seems to kind of make sense in this limit, but answering this question is equivalent to finding this. You can transform one or the other and proceed. What is this? Does anybody know how to do it? Or I'll just be real specific. I'll put down a v right here, just to denote what that function is. And we want this. So I want the implied prior on the variance. I want to think about it on this other scale that I have some familiarity with. It's pretty easy to do. So all I have to do is I just need to make a note that my transform is phi is equal to 1 over sigma squared. So every time I see a phi over here in this equation, I plug in 1 over sigma squared, or 1 over v, you might say. This is 1 over v. So now I've got 3 notations running around for the exact same parameter. There's another one I can think of too. If I think about it just as a function of sigma, and not sigma squared. We'll talk about that in a moment. We're going to see something really cool. So what is this? I take my function of phi and I evaluate it at v right here. So I'm going to plug this in that every time I see a v right in here, I'm going to plug in 1 over v. We're going to do that. There's also this other term that we need to multiply by. We'll write down that in a second. But what this is this is 1 over 1 over v. So pretty easy substitution. What is this thing? This is d 1 over v dv. The reason I switched to v is because if I had sigma squared down here, I'd have a d sigma squared, and I might misinterpret that squaring operator, which is really just telling me it's the variance. It's squaring something for a second derivative operator. So sometimes the notation gets a little bit messy with the squares. What do they represent? Is that a second derivative, or is that squared? That's the reason I did this right here. We can do that derivative. Pretty easy, right? So this thing is just v inverse. How do you do it? Bring down your exponent, and decrement your exponent. So bring down my exponent, v minus 2. Is that right? So this is 1 over v squared. The negative sign right here that popped out, you've got this absolute value sign that takes care of everything. So this is very shorthand chain rule that happens in the transformation formulas that we normally use. So if you've ever wondered why is this thing here, because we're shorthanding the chain rule. I go back to the fundamental theorem of calculus and see what really happens. And so this is a nice convention for us to follow. We know it needs to be positive because it's a density as well. So that's the intuitive answer, but really it's the chain rule and the fundamental theorem of calculus. Hopefully somebody's taught you that really well. We could probably do review sessions on transforms. I usually find it useful for you guys to get a refresher, so I might put something together. We can finish this analysis. Think about what this thing is. So this is v right here. Times 1 over v squared. This is 1 over v. That's kind of cool. So I want you to see something that regardless of how I scale this distribution, our prior on phi is 1 over phi. So phi is acting as a scaling parameter. And my prior in this case, through the conjugate limit, was 1 over phi. And that's equivalent, if I would have done analysis on the variance, is equivalent to this prior 1 over phi. So I could have started with the variance formulation of the likelihood, multiplied by this prior, worked out what it was. It would be an inverse gamma, and it would tell me which inverse gamma it is. That analysis would be exactly the same as this analysis that we just did. So it would be one-to-one with each other. One's an inverse gamma on variance. This is a gamma on precision. And that's a one-to-one transform, so those analyses would be equivalent. So if you're operating with variance, you use this prior. I'm operating on precision and I use this prior. While our answers look different, they're identical to each other. They're isomorphic, they're the same things. I can transform one to the other. Here's another question. What's the implied prior? For sigma. That's a different parameter. It's not sigma squared, this one's sigma. So if somebody's like, no, I hate when people talk to me about sigma squared and variances, I prefer much more for you to talk about sigma, the standard deviation. That's fine. So they're one-to-one with each other because it's all positive stuff, so we don't have to worry about it. Does anybody know what the answer is? Try to work it out in your head. Same sort of thing. I just go back to this thing, rephrase what everything is in terms of sigma, plug in the sigmas, and work through the Jacobian. I'll leave that as an exercise for you to do. Turns out it's this, 1 over sigma. So identical to doing this, you will work out this. So let's just make a note. Try this at home. Here's a template for your math right here. So it'll be 1 over sigma, 1 over the scaling parameter. So it's kind of neat that with scale parameters, if you like this parameterization right here, then you like this and you like this. They're all equivalent to each other. They're the same things in disguise. But I want to dwell on this parameterization right here, 1 over sigma. Now I want to remind you that what we had found for scale distributions, for location scale, I wrote down this transformation a couple days ago. So that's my location scale transformation. It's just a line, linear transform. Here's the scale. Here's the location. If I have the distribution for f of x, I know how to transform it to get the distribution for fy. So fy, right here, usually I cap these just to be specific, was 1 over sigma fx. What did I plug in right here? I had to back solve for x. So this was going to be y minus mu over sigma. That's just another name for x. So this right here is the derivative term that pops out. It's 1 over sigma. So when I think about things using sigma, the correct thing to do to make these two distributions really the same thing, they're presenting the same information to each other, is I have to scale everything by 1 over sigma. That is the natural thing to do. So when you're trying to be invariant to scale, you always have to introduce this 1 over sigma term. It's not a coincidence that the prior that we just got right here is 1 over sigma. It turns out this is a transform invariant prior. We will talk about that soon. That's the Jeffreys prior. And so even though I came up with this through a conjugate limit, these priors are mathematically more important than that. It's not as arbitrary as it makes it seem. But I want you to just think about this a little bit. That for mu, when I wrote down the location scale thing, there wasn't a term in the Jacobian right here. And the prior that we induced through the conjugate limit was the flat prior, proportional to 1 or proportional to some constant. It's not a coincidence that this is popping up as a factor of 1 right in front. I didn't have to do anything with mu. So a lot of ways to think about it. And so that prior right there, the flat prior is shift invariant, meaning I can shift it and I don't change the information about the mean. So there's all these neat mathematical things that collide. And so if you're into mathematics, you might think about this a little bit more. But that thing I showed you previously, where we have this in the transformation, this term, 1 over sigma, it's not a coincidence that we wind up with that 1 over sigma as well. So this is a scale invariant product right here. This is what scale invariance looks like regardless of how I parameterize the scale. So it's 1 over that thing. So it means that if I multiply it by some arbitrary constant, let's call it C, and then I compare it to another point, let me just write this down. It's be hard to say, so let me just write it down like this. Shift invariance. This means, so I'll say for mu, so my prior on mu, this was proportional to a constant. Right here, I usually make that constant 1, but I'll just make it C in this case. So shift invariance means I can take whatever this thing is, I can add a number to it. So I'm going to call my number delta. And then I can compare it to this function evaluated somewhere else. So I'm going to evaluate this at 2 different spots right here. I'll just say, this is my number C right here. And I'm going to evaluate this at mu1 and mu2. Flat, so it's the same number right here. So this is going to be the same as just this pi mu1 minus pi mu2 in the same place, in the first place, C minus C. Shifting it by delta didn't do anything. Why did I use subtraction right here? Well, this is an additive parameter. And so I have to operate under that same rule, that operator. For scale invariance, we might do something like this. 1 over, I'll do this as phi. So this is our prior for phi. I'm going to evaluate this at a point, and I'm going to compare it to another point on this same thing. So this right here is just pi phi1. Here, 1 over phi1. This is 1 over phi2, or pi phi2. And this is just going to be 1 over phi1, 1 over phi2. So I'm trying to tell you something that at least what invariance means. What invariance means is I can multiply it by something and I don't change anything in the problem. Mathematically, it means that those 2 deltas cancel each other. Lots to think about there. So this isn't a deep measure theoretic class on Bayesian statistics, but I want to point out some things that are at least mathematical curiosities. What I really want to do is I want to convince you that this prior that we just came up with makes a lot of sense. For mu, it made a lot of sense to us intuitively. Everybody understands adding a lot better than they understand multiplying. Everybody understands shift invariance by slide this back and forth. The precision parameter, we came up with a very similar set of mathematical properties for this parameter, but it's on a multiplication scale. So you just have to think about it a little bit differently. Anyway, I'm never going to test you on that, per se. But it's fun to think about. Okay, so let's do something else. Let's do the joint analysis now. Keep saying we're going to do it, so we might as well do it. So joint analysis. Mu. And my favorite way to parameterize this problem, phi. And it's an arbitrary choice, but A lot of us in the States use this arbitrary choice. It's just convention. So we want find pi mu phi. The question is, when we do this, we know what the likelihood function looks like. We've written it down over and over again. What priors do we use? I'm going to argue, at least for the moment, let's use those priors we just came up with and have a long discussion about them. Proportional to 1, proportional to 1 over phi. Going to be my priors on mu and phi respectively. So this is going to be just this thing. Likelihood, phi to the 1/2, can't get rid of that because that's part of the likelihood. Doing a joint analysis. E to the minus phi over 2, x minus mu squared. So that's my likelihood times pi mu. I've been extremely specific that these priors right here are conditionally independent of each other. And we had argued that as we developed those priors in the first place. Maybe we don't need a joint prior on this. I don't have any way to encode that joint information without knowing something about the problem. So I'm just going to pick our conjugate limits right here. These were both improper priors. I'll remind us, everything worked out fantastic when we used them last time. At least I made it seem like they were fantastic. I would choose them. I would have felt pretty good about that analysis. If you walked in with your one data point and said, what do you think? I give you a posterior on it. If you could give me mu, I'll give you a posterior on it. You can give me phi, I'll give you a posterior on it. And I would actually hand that answer to somebody and say, that's the best I can do. So they might come back and say, well, now I want to know about both of them simultaneously. And the posterior distribution looks like this. So this is proportional to posterior. So this is just phi 1/2 minus 1. This is the minus 1 right there. Same thing. E to the minus phi over 2, x minus mu squared. So this would be my posterior distribution. What do you think of it? Looks pretty good, right? So that's a joint distribution over mu and phi. So it's a probability distribution maybe over mu and phi. What is that distribution? Can you recognize it in mu and phi?
Another gamma.
What's that?
Another gamma distribution.
Yeah, it kind of looks like a gamma. In phi it looks like a gamma. And in mu it looks like a normal. So it's this joint distribution where the margins you kind of recognize, or the conditional forms you recognize. Jointly, what is this thing called? I don't know, I call it the normal gamma thing. So I come up with a name, but there's no name for it. Nobody's devised the name of this distribution. Maybe a normal gamma distribution. So that Bayesian thing, when you do the conjugate analysis, that distribution. So this isn't named very well in 2D, but we understand it one-dimensionally. So would you give this answer to somebody? I personally would not, and I'm going to show you why in a second. So I would give you the full conditional for mu. If you give me phi, I'd give that answer to somebody. If somebody came in, told me what mu is, I'd give them the distribution for phi that we just discussed. I wouldn't feel too bad about it. I'd say, probably should go get another data point or two, but that's what you got. Here's your answer. This one right here, I want to discuss a little bit more. Let's just think about this. So question, what's pi mu given x? We left off with this last time. This is going to be equal to the integral over the joint where I integrate out. So this is the margin on mu. I've marginalized out phi. That's what's left in the margins. It's like this contingency table language that we use. But that's how you marginalize. I've been really clear about my notation that every time I have phi, I put it in. So this means something very different than when I condition on phi. Does anybody know what distribution this will follow? I want you to think about if you're in Stat 101 class and somebody asked you to do inference on the mean and they gave you the variance. You would do some sort of normal distribution analysis. The Bayesian does that as well. They base their inference off of the normal distribution. In Stat 101 class, you run to your C table. Normally distributed table doing inference if you know what the standard deviation of the variance is. If I take the standard deviation away from you, you have to estimate it, then in Stat 101 class, you run off to the T table. So you do a T analysis. So that might incline you to think that this distribution is T. So there's at least some intuition. Let's see. So this thing is going to be proportional to, I'm pretty lazy, I don't like working out my normalizing constants up front. So this is proportional to the likelihood on phi and mu. There's no reason I spun those around. I'm thinking about it, it's exchangeable. So I just did it for no great reason. Times my priors. Pi mu, pi phi, t phi. Definite integral, I'm going to integrate out all of these. So I'm averaging over, I'm giving you an average answer on mu. That's what that means. So this thing right here is equal to 0 to infinity, my likelihood function times my prior. So we can do that. I'll just take this thing and I'll plug it in. So this is that function right here that we're putting into our integram. So this is phi to the 1/2 minus 1, like the phi the best is phi I can write, minus phi over 2 x minus mu squared dphi. Can you do that integral? How do you do it? If you got this in calculus class, what technique would you do? Yeah, it looks like a Parks problem. So you'd probably try to figure out how this thing works with like some integers in there, and you try to generalize that formula. Be a little bit of a challenge, but not too hard. I'm going to do it extremely different. So I know that this is a kernel. I'm integrating over phi, so I'm operating on phi. This right here is the kernel of a gamma. And I can even recognize which gamma it is. So how do I recognize it? I look right there. This -1 is always there in a gamma distribution. And so that's this parameter, alpha tilde. I'm going to call this 1/2. This is beta tilde. Where do I look for it? I look at the thing that's multiplying by phi right there. So how am I doing this? I'm recognizing what a gamma distribution is. So this thing right here is x minus mu squared over 2. I've used the conjugate limit, so those hyperparameters alpha and beta we were talking about before, they've already been taken to 0. That got taken to 0 as soon as I plugged this in for my prior one. So I know what this integrates to. If I only have the kernel, it integrates to the inverse normalizing constant of the gamma distribution. I told you a moment ago we should remember what that looks like. And it'll save us from integrating by parts. We have a huge advantage in this class that most of the stuff we integrate integrates for 1. So I know distributions integrate to 1. So if I have everything but the normalizing constant, then I know the kernels will integrate to the inverse of that normalizing constant. So let's look at this. What is this thing? Normalizing constant. Go back and look at my notes just a moment ago. The normalizing constant looks like this. We need the inverse of that. Just back to our basic probability class, how we find these things. So this integral is equal to gamma alpha tilde over beta tilde, alpha tilde. So that's my thing right there. So this is going to be gamma to the 1/2, gamma 1/2, and this is going to be x minus mu squared over 2. And then I raise this to the 1/2 power. That's my alpha tilde. So there's my integral. This is my distribution on mu. So this thing right here is pi mu given x. Proportional to it. Yeah, I might want to think about what the normalizing constant is. We'll do a little bit of extra simplification. This is just a number. Everything I've done is written up in proportionality. You might even know what that number is. It's a fascinating number. But not relevant in our conversation right here. So what does this thing look like? We can get rid of that. That's part of the normalizing constant. That's part of the normalizing constant. So as a function of mu, it's just this part. 1 over x minus mu squared raised to the 1/2 power. This is 1 over x minus mu absolute value. And I could normalize this if I felt ambitious. So x and mu for elements, negative infinity over infinity. If you go to normalize, so sorry. So I just did some replacement right here. If I go to try to normalize this thing, it's improper. So for the same reason that integrating 1 over phi. So if I try to think about this as a function over mu, and I integrate across mu to normalize it, the normalizing constant blows up. So this is improper right here. Try to clean up these notes a little bit. Again, I'm not offline for you guys to review, but I think it's worthwhile to see how you see it all written out. What do I do with this posterior distribution? It's improper. I argued for a long time I don't really mind if my priors are improper. How do you feel about improper posteriors? It's not a probability analysis. Bayes is supposed to give us a probability distribution. And by using these improper priors, I just wound up with an improper posterior. And if your posterior is improper, it is useless. It doesn't do anything for you. Improper priors, they're very regularly used. So my question for you is, what would you do? So say your client comes to you, asks you for joint inference, they give you X, didn't give you mu or phi, and ask for the distribution on mu. You say, well, I've given you this thing that's not a probability distribution. It doesn't normalize. Tails are too heavy. So I'm going to make a suggestion. What would you suggest to do?
Get one thing.
I love it. So usually, so 14 years, you're the first one to say this. Did you watch my old videos on this? You're a smart guy. So get more data. Some people might be inclined to run in and say, well, let's make the priors proper. And if the priors are proper, your posterior will be proper. You can prove that later. Prove it maybe at the beginning of next time. And so you probably wouldn't want to anchor information and inject it into your prior, because that's kind of cheating. And so you didn't know anything. So the answer right here is you need to get more data. So if you want to do inference on the mean and the variance, and you only have one data point, It's not enough information. And I kind of really like this answer because the Bayesian analysis has kind of told us this. There's something to think about right here. We probably shouldn't be doing this inference on the mean and the variance or precision, however you think about it. So I want to come back next time, look at what happens when we get more data. And here's just a tidbit. The distribution does become T as we get another data point. So we need at least one more data point to do this analysis. We'll do it as a function of n, and this distribution does work out to be T. So it turns out this term right here, as long as you have two data points, ends up looking like the kernel of a T distribution. So a very valuable thing you can do before Wednesday is go to Wikipedia and look at what a T distribution looks like. Then I'll pull it out and we'll show that that thing starts going towards a T distribution as we get more data. That's it for now, you guys. Thanks a lot.